everyone. Welcome to episode number 686 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by me, Amelia Dalton. Artificial intelligence is moving faster than ever, but as AI models continue to grow in size and complexity, the challenges surrounding inference performance are becoming impossible to ignore. Delivering fast, efficient, and cost-effective inference remains one of the biggest hurdles standing between AI innovation and widespread deployment. ElastixAI CEO Dr. Mohammad Rastegari joins me this week. We chat about how we can overcome those challenges and why a different approach to AI infrastructure may be needed. We also explore the key bottlenecks limiting inference performance, how ElastixAI is tackling these issues, and why FPGAs are emerging as a compelling platform for accelerating large language model inference. So, without further ado, please welcome Mohammad to Fish Fry. Hi, Mohammad. Thank you so much for joining me.
Thank you so much for having me.
First off, what do you think are the primary obstacles hindering AI inference performance?
Yeah, that's a question that I'm sure these days many people and companies are trying to understand it in a deep way. So let me first go back to a long back history, but it's the recent history of AI and how it evolved. So if you remember, prior to this type of AI that we are seeing, like ChatGPT and the rest that people can freely and really feeling an AI, before that the most intelligent system that we had was a search engine, and people wanted to search with Google and try to get the answers from the search to be as intelligent or as smart enough for them to basically get their answer from that. And then for the companies to make it smart and intelligent, they had to rely to lots of data. And the hard part of it was how they can very quickly go through a massive amount of data and retrieve information that actually answers very intelligently to the query that user is asking. I mean, those topics and those era of AI was very different than today. The actual model that tries to find the answer was not that big enough. It was like a small model, but then its job was to actually go deep into the lots of data. And then the part was important was how you could shrink the data to become more compressed and easy to search or have a good structure for that. And that was to the extent that some of the very famous professors, one of the one that was mine was Alyosha Efros from Berkeley, who believed that actually the intelligence will be solved if we can save all the data in the world and have a mechanism to very effectively access them. That was an algorithm back then called k-nearest neighbor search, and say that with this we can solve entire intelligence problem, and AI will be solved with that. As times goes by, so the deep learning or neural network shaped up, the trend was that rather than keeping data separate from the model, was that actually let's bring data into the model. So the AI model, the parameters of the model, they become actually your data, the source of the data. And then when inference happened, basically your query and inference happens, you had to have a good way of actually now searching within your model. Now, instead of having more compact data, people are thinking to having a more compact model or a more efficient way of accessing the model. So that's the whole key problem here. There are lots of computes happening within accessing the model, and also the access itself is a problem. And through lots of progress in hardware, we're in a good position to actually see lots of computes are available through the GPUs of the modern, the GPUs of today, like H100, B200s. They're offering a tremendous amount of computes so that the computes are available. And then one of the other things is that the memory technology also have progressed fast, so that the access to the actual the model's parameters are becoming also quite fast. But then still, the part that is the more challenging is the balance between these two, not the actually having one of them here and or not having? Actually, what's the right balance? And then what is the right adaptation? Like, how we can, because, the actual like modeling in the AI is keep evolving, the type of data structure and everything. But the hardware behind it, in terms of offering the amount of compute and memory access, is great. But then they are not they cannot be adapted to the actual precisions or the models that we have. And that's the main challenge that we have. We may have like some models with today's hardware work perfectly, but then the next model comes, it doesn't work and it's not as efficient as possible. And we have to, design a new hardware for that. So that's basically the main issue with the inference today. Like you have a query and you have to run billions of computes and you have to access to billions of parameters, and every day is the pattern of this will change, the type of the data and everything will change, and you have to adapt yourself to that. And that's the biggest problem that we have today.
So ElastixAI can help solve these issues, right?
Exactly. So one of the basically we're trying to like attack the core of this problem, how like we can be more adaptable. So to put it in this frame, that in today's like work of optimizations in AI and inference, we have usually two folds of companies or two folds of methodologies. Ones that they're trying to optimize the software or ML on top of the current hardware. They assume that the hardware is fixed. Let's just find a good solution for this hardware. And the other ones are the one that they say that, okay, let's just go assume the ML and software are fixed and let's design a better hardware. So, and both of them has their own pros and cons. Let's just look at the cons of each of these two. So the cons of assuming the hardware is fixed is that, okay, by assuming that the hardware fixed, let's define like ML that fits for that hardware, is that basically that limits your hand in terms of thinking out of the box, thinking about like more like, advantages, like, optimizations here that you can think of, like, maybe that hardware doesn't support, but then it can like be more effective in the actual utilizations of the efficiencies that you are, or optimizations that you're bringing on the table. And on the other hand, if you assume that, okay, let's assume ML and software are fixed, let's just design a better hardware. And that's also like, even based on today's progress in AI, is so wrong, because we are yet far from achieving or being in a position that the development of AI being saturated. Every day we are seeing new workloads are shaping up, like new optimization methods are coming up, and you can, by no means you can assume that these are fixed and go, let's design a hardware, and you have to spend hundreds of $1 million like in capex and wait for a few years that hardware to show up. By the time that the hardware are there, already ML is in a different world. So both of them have this problem. So now to attack this, we need to like have basically a solution that, rather than assuming that, hey, let's conform our software to the hardware, we should have a solution that's be some like, to bend the hardware or conform the hardware to the progress of the software. Basically, we have to, at the same time, in parallel, like operate by optimizing hardware, software, and ML, all with the same speed. So that's why we're building a reconfigurable like machine learning platform that actually is a true co-design of hardware, software, and ML. And that's all the core about the Elastic to solve that.
So let's talk about FPGAs. Now, why should we consider FPGAs specifically for LLM inference?
That's a great question. So FPGAs are great hardware, not because they are a better hardware than current inference hardware in terms of their specification. It's all because they are adaptable. So used to like, FPGA have been used for prototyping in new hardware. And the beauty about it was that, they had this structure that you could actually program the connection in transistor level to to shape up a new hardware with that hardware. So, and back then, when the AI model were smaller and, there were like tons of different type of model and everyone wants to train their own model, it didn't make sense to use FPGA as a commercial scale solution for, let's say, AI inference. But nowadays, in the same way that it happens to GPU become a good solution for training, we think that FPGA happens to be in the perfect sweet spot for AI inference. So why and how? It's because, today kind of like, the general architecture of the LLM, like as a transformer, is like kind of like saturated. Everyone knows that, okay, this is the major architecture. But what's evolving is all the optimization around it is very fast evolving, and the very pace of it is very fast. And then the core structure of all of these AI models are very simple, like just matrix multiplication in different sizes, different dimensions, and so on, and very few like functional operations there. And that's it. And then all it matters now how you put those operations together to shape up a new architectures. And then that's the core of it. And then this simplicity makes the part that, okay, if we have a reconfigurable hardware, the cost of reconfigurability may not be as huge here, but then all the benefit that we get from the reconfigurability, that we can enable new optimization, new, let's say, data structure and everything, all the way to the data flows that could be native to the hardware without the need of building a new silicon. This is a huge advantage that we have. So it's basically as if we are building a new silicon, but without going to the TSMC and put in order for a year or 2 years to get all those verification and being worried to scale up the hardware. Are we able to scale up the hardware and so on? And then we can get all the benefit of the optimization. So that's actually the beauty and what's good about FPGAs and how they can help us to actually be very successful in AI inference.
So, beyond LLMs, what other types of AI models or workloads do you think are particularly well suited for optimization using your platform? And what does the roadmap look like in terms of these supporting emerging model architectures?
LLMs, they are, again, as I mentioned, they're a transformer type of neural network. So I'm usually defining the workloads in this way. And we have workloads that they have token as an input and token as an output, meaning that as an input, you can have text, speech, image, or videos. And then as an output, you can have text, speech. These are tokens. And can be easily represented as a token. But then generating images and videos, they're different things. So, and the underlying architectures would be a little bit different from an autoregressive, let's say, LLM type of transformer that we have. They are basically based on stage-by-stage generations of the images and videos in different forms. So that the key architecture there is a little bit different. And then the reason we are attacking LLM today because there are literally a few LLMs in the markets in AI inference holdings for the shares of like billions of dollars per year. And the regularity and the market definition around them is extremely well defined. On the other hand, image and video generations are lots of concern around them, privacy, and the market size is not as big. However, the opportunity is huge there too. And because of those, we decided first to focus on this. And then we can enable those after we are being like successful with the LLM itself, and nothing will stop us. Again, as I mentioned, the general structure still is transformer, but in a different form. Then when it comes to like, the roadmaps, I mean, what we're seeing here, actually, we want to see like one step further. Our vision here is that once we show that, let's say FPGAs or a reconfigurable hardware platform is a viable solution at large scale for inference, then we let the AI builders who are building new models, training new models, spends billions of dollars to train new models, to actually be open to change their data type, their data structure, or their architecture to be more suitable for this type of hardware. So right now, they are not doing many things because they're afraid to put that risk on, and then there's no hardware to benefit from. And once that be solved, then they use it. And then once they use it, then that become the solution. And there's basically that become like the sticky point of the solution that is out there. So, and it totally makes sense. As recently you may have seen that, Jensen was mentioning that, hey, one of the challenges that they have that they are not selling their GPUs, let's say, to China and the other countries is because they're afraid that if they like China and the others would start like building their models and optimizing for their own hardware. So now at that point, then our GPUs will not be used for Chinese models which are open source and people are using it and so on. And that's it. But then FPGA can exactly break that rule, because now that's reconfigurable. We can adapt ourselves to any optimizations that like all the silicon is supporting there. So those are basically the real challenge in the market. And our roadmap is that to actually show that we get to the time that AI builders actually see more than whatever is out there in today's AI hardware. And they can think really out of the box and adapt all the optimizations that even we are not aware of it, but by the time it's there, we can quickly adapt ourselves to it.
So AI is innovating by the day, it seems. So what do you think is the core factor that you believe will sustain Elastic AI's edge in this evolving AI infrastructure landscape?
Yeah, the key differentiating factor is exactly when this power of adapting to the changes, meaning that assuming that an AI builders, one of the famous one, I'm just putting just a random name here, Anthropic or OpenAI or whoever, just, they decided to build a new model with a 2.5-bit quantization with a technique that basically is supported by an FPGA or inference platform in Elastics. And then at that point, the key differentiation for us is already there. It means that no one else in the market can actually generate tokens with this inference precision. And then that's just the beginning. So now it basically all the ML optimizers, like there are like tons of ML optimizers incorporate that they are right now their heads down as in PyTorch, which is a high-level language that they design their optimization. They all mostly are confining themselves by whatever NVIDIA is providing to them. And by that time, then they don't have to think about that. Then they're in PyTorch land, and then they can think about any optimizations. And, as a matter of fact, we have some of them today. Like Microsoft, a few years ago, they released that paper called BitNet based on LLM. It was a 1.5 bits, like LLMs. And they were asking in the last hardware manufacturer, please make a hardware that can support for this operation. So now we have lots of those ML optimizers that their hands are tied with whatever NVIDIA is proposing to them. By the time that we are there and we have like all those like LLM optimizer adapted to our platform, then we are immediately differentiating ourselves from all the like other providers of the LLM inference.
All right, Mohammad, it's time for your off-the-cuff question.
Yeah.
So, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
That's a great question. I would have a fried mussel from a specific restaurant in Italy, in Genoa. It's called Zena. I love that fried mussel. It's one of the best food I have never had experience anywhere else.
I love it. It sounds amazing. Awesome. Well, Mohammad, it was a pleasure speaking with you. Thank you so much for joining me.
It was a pleasure for me too. Thank you so much for having me.
Well, folks, that's all I've got for this week's Fish Fry. But if you'd like more information about the topics covered in today's show, check out this week's Fish Frying page on eejournal.com or this week's episode on YouTube. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EE Journal. If LinkedIn is more your thing, I dig it. You can follow us or me on LinkedIn. And we are also on Blue Sky Social and Mastodon as well. And we have a YouTube channel, youtube.com/EE Journal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me. And of course, you can subscribe to our EE Journal YouTube channel as well. Thank you, everyone, for tuning in. If you know of any cool new technology or heck, you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of June 12th, 2026, I'm Amelia Dalton, and you've been fried.